At this point, we know what the determinants of all of the elementary matrices are, and we also know the effect of elementary row operations on the determinant. This actually gives us a lot of insight into, or it can give us a lot of insight into the determinant of a matrix, because remember that every matrix A, we can express it as the elementary matrices that reduce A to its reduced row echelon form times its reduced row echelon form, right? If we start with the matrix A, I guess I've named these a little differently, so we can do a row operation by multiplying by some elementary matrix, right? Then we can do the same thing for the next elementary row operation, and so on. And once you've done all of these elementary row operations, then what you get, so this big product, is the reduced row echelon form. But all of these matrices are invertible, so we can multiply by each of their inverses to move them all to the right. The inverse of an elementary row operation also is an elementary row operation, or sorry, the inverse of an elementary matrix is an elementary matrix. So if we just put everything on the other side and rename it, we get an equation like this. Okay, so every matrix is its reduced row echelon form times a bunch of elementary matrices. So let's think about, what does this tell us about the determinant of a matrix? Well, the matrix A is, right, this first elementary matrix times a bunch of other elementary matrices. Okay, times the reduced row echelon form. And what could this first elementary matrix be? Well, there are three possibilities. Either it's a row interchange, right? And what is the effect, if it's a row interchange, what is the effect of this row operation? Well, if it's a row interchange, the effect is to switch the sign of the determinant, right? So if we unswitch those rows, that's the same as removing this row operation. That's the same as having a minus sign out here. Okay, so we get that. But this is the same thing. Let me write it this way. This is the same thing as, right, this -1 is the determinant of a row change. So if E1, if this first elementary matrix is a row change matrix, then this -1 is the determinant of a row change matrix. So times the determinant of all the stuff that's left. Times the reduced row echelon form. Okay, the second possibility for E1 is that it multiplies a row by some constant C. Well, in that case, this determinant of all of these E1 through EK times R is, right, the effect on the determinant of multiplying a row by C is to multiply the determinant by C. So C times the determinant of E2 through EK times R. Okay, but look, if E1 is multiplying a row by a constant, what is the determinant of E1? Well, it's C. That's what we figured out. So this C is the determinant of E1 times the determinant of all the rest of it. E2 up through EK times R. Okay? The last possibility is that this elementary matrix E1 is the matrix that adds C times row J to row K. Right? But if that's the case, what does that elementary row operation do to the determinant? Well, it doesn't change the determinant. That's what we figured out. So this is 1 times the determinant of E2 through EK. But if E1 is the elementary matrix that adds C times a row to another row, 1 is the determinant of that matrix. That's what we figured out. So this is determinant of E1 times the determinant of all of the rest of it. Okay. Now, notice that we started with the determinant of A, and what we got is the determinant of the first elementary matrix times the determinant of the rest of them. But we could play this whole game again. So we get determinant of E1 times the determinant of E2 through EK times R. But we can do this again, right? What we just proved is if you have a matrix, you can, the determinant of the matrix is the determinant of its first elementary matrix times the determinant of the rest of it. Okay, well, we can use that result again on this, E2, EK, up through R. So we can write that as the determinant of E2 times the determinant of the rest of it. E3 up through EK times R. Okay, but you can see we can keep doing this over and over again. As long as we still have elementary matrices, we can always break them off one by one. So what we get here is the determinant of E1 times determinant of E2 and so on, all the way up through determinant of EK times the determinant of R. Okay, so on its own, this is a pretty interesting result. The determinant of a matrix is actually just the product of the determinants of all of the elementary matrices that make it up times the determinant of its reduced row echelon form. But wait a second. What are the possible values for the determinant of a reduced row echelon form? So R can only come in one of two forms, right? So for R, there are two cases. The first case is the reduced row echelon form of a matrix might be the identity matrix. Remember, this whole thing, whenever you talk about determinants, you're talking in a context where your matrix has to be square. And so your reduced row echelon form might be the square identity. And the determinant of the identity is 1. So it's possible that this determinant out here at the end is just 1. The second case is that your reduced row echelon form isn't the identity. But if you have an n by n reduced row echelon form and it's not the identity, it has to have a row of all zeros. So last row must be all zeros. But if you take the determinant of a matrix whose last row is all zeros, if you expand the determinant across that row of all zeros, then you get 0 for the determinant. So the possible values for this determinant at the end here are either 1 or 0. So the determinant of a matrix is the product of the determinants of these elementary matrices times either 1 or 0, depending on whether the reduced row echelon form is the identity or not. Okay, so that's pretty interesting in its own right, but the reason that this is really important is because it lets us show the following. The determinant of a product is the product of the determinants. Now, if you just wrote down the formula for each of these, right, if you wrote out Aij and Bij, and you wrote down, expanded each side here in terms of these matrices, actually proving this would be a complete nightmare. It would be very, very, very difficult to keep track of all of the indices and all the minus signs and everything. It would be a complete mess. But we know a lot about determinants, and in particular, we know a lot about how the determinant interacts with reduced row echelon form and elementary matrices. So let's write A in terms of its elementary matrices and reduced row echelon form. So write A is a product of elementary matrices, E1 through EK times R, and R is in reduced row echelon form. Okay, let's calculate the determinant of A times B. Okay, well, there are two cases. And the two cases are depending on the two possibilities for the reduced row echelon form of A. So the first case is that the reduced row echelon form has a row of zeros. Okay, so in that case, the determinant of what we're going to do is, in this case, we're going to calculate this left-hand side, calculate the right-hand side, and then just see if they're equal. So on the left-hand side, we have the determinant of A, B, but that's the determinant of E1 through EK times times R times B. Okay, now what we showed about the determinant and elementary matrices says that this is the determinant of E1 times the determinant of E2 and so on, all the way up to times the determinant of EK times the determinant of R times B. Now let's think about this product, R times B. Remember, R is a matrix whose last row is all zeros. If you do a product where on the left the last row is all zeros, what do you get in the last row of the product? Well, no matter which column you choose here, right, when you take a column, put it on its side and sweep downwards, when you hit this last row, you get 0 times everything in this column, so you just get zeros. So that means every entry in the last row of the product is zeros. So R times B has the last row is all zeros. But we've seen that the determinant of a matrix whose last row is all zeros is 0. So this last determinant is 0. So the whole thing is 0. All right, so in this case, the determinant of A times B is nothing, is just 0. Okay, now let's calculate the determinant of A times the determinant of B and see what we get. Right. These are supposed to be the same, so hopefully we get 0 again. All right, well, this is the determinant of A. Sorry, no, that's not what I want. This is the determinant of E1. Sorry, what I'm doing is writing A. A is E1 times E2 all the way up to EK times R. All right, so that times determinant of B. But again, what we know about determinants and elementary row matrices is that this is the determinant of E1 times the determinant of E2 and so on, all the way up to the determinant of EK times the determinant of R, and then times the determinant of B at the end. But R has a row of all zeros, so this determinant of R, that's 0, and so this whole thing is 0. And so we see that the determinant of the product is the same as the product of the determinants. Okay, so we verified this when R has a row of all zeros. So what's the other case? Well, if we have a reduced row echelon form and there's no row of all zeros and the matrix is square, then that means that the reduced row echelon form is actually just the identity matrix. Okay, well, in that case, let's again calculate the determinant of AB and the determinant of A times the determinant of B and see what we get. So in this case, we get determinant of E1 through EK times the reduced row echelon form, but remember, we're assuming that that's the identity, so we don't need to write it. There's no reason to write the identity in here, times B. But we know that we can break this determinant of elementary matrices into pieces, so this is determinant of E1 times the determinant of E2, and so on, all the way up to the determinant of EK times the determinant of B. But, you know, just like we broke this determinant apart because it has elementary matrices at the beginning, we can now take these, everything except the determinant of B, and put it back together, right? Same thing but backwards. So that gives us the determinant of E1 times E2 all the way up to EK times determinant of B, but the determinant of all these elementary matrices is just all of these elementary matrices, the product of them all is just A. So determinant of A times determinant of B. So we finally showed that the determinant of a product is the same thing as the product of the determinants. And this is really a big surprise, and this is also one thing that makes the determinant surprisingly important. Just to do a calculation that demonstrates this, I'm just going to pick random numbers, so there's nothing special about the numbers that I'm picking here. Let's do 2, minus 3, 1, 4, and I don't know, how about 5, minus 1, minus 4, 6, I guess. Okay, so let's work out the matrix product. So 10 plus 12, so 22, and then 5 minus 16, so minus 11, and then minus 2 minus 18, so minus 20. I should have picked smaller numbers. Minus 1 plus 24, so 23. Uh-oh. I'm going to have to multiply some big numbers. This is going to get embarrassing. Okay, so now what we can do is take the determinant of these individually. So down here I'm going to write determinant of this one times determinant of that one. So I'm going to calculate their determinants and then multiply. So this first determinant is 8 plus 3, so 11. And the second determinant is, oh boy, 30 minus 4, so 26. Okay, now let's compare that to the determinant of this thing. So let's see, 22 times 23 minus negative 20 times negative 11. Okay. I'm going to grab a calculator because you don't need to watch me multiply numbers. If I were better at math in my head, I could just do that in my head. Okay, 22 times 23 minus negative 20 times negative 11. I get 286, and 11 times 26, that's 286. Okay, so I just picked random numbers, so the chances of this happening by chance are pretty small. So hopefully that's, somewhat convincing that the determinant of a product is the product of the determinants.